Hello, class. This is Mr. Hart. In this podcast, I want to go over the kind of subchapter we discussed about the center of mass. Okay, so center of mass is a key concept that sometimes gets overlooked, and so I want to go through and make sure we understand what it is, why it's important to the calculations we do, and really just get a good concept of how it affects physics. Okay, so we watched this demonstration of this kind of cone going uphill. Okay, we watched this video of how instead of going down the hill like you would expect something being pulled by gravity to do, it actually goes up in the other direction. Okay, kind of a weird phenomenon, but it has to do with the center of mass. So we'll come back to it in a second, um, and we'll see why that works. Okay. But the first thing we did was we looked at a video about a slinky drop from Veritasium, so I highly recommend it. But the question is, um, when you watch this video, he asks if when he drops that slinky, is the slinky gonna kind of compress itself to the bottom, or have the bottom come to the top and then fall? Is the top gonna go to the bottom of the slinky and then fall, or is it gonna fall stretch? Is it gonna have the top and bottom meet in the center and fall? Okay, so he's trying to ask what's going to happen. Okay, what's going to happen to the slinky when he drops it? And it's hard to answer that with our current understanding of physics. Okay, but it's a good question to think about. So think about in your mind, which one would you say would happen? Okay, a lot of students think that the top and bottom will meet in the center and then it will fall. Okay, but the answer actually surprises most students. It actually will fall, or the top will go to the bottom first and then the whole thing falls. And so, again, if you want to watch the answer, it's at this link. It's a really cool video, slow motion of the slinky dropping all the way to the bottom, or compressing all the way to the bottom and then falling together. Okay, there's also, he does one with a giant slinky, and it's really quite incredible to see because it almost looks like the slinky's floating. Okay, it's quite amazing. And so we kind of ask, how can this work? How can this be? And it all goes to this idea in physics, okay, that all objects' movements are determined for the center of mass of the object. Okay, that's the underlying assumption we're making when we do Newtonian physics. Okay, so something like a slinky that has a shape, it can compress and stretch. We don't really deal with objects like that very much, but we know that we can look at the center of mass and determine the movement for the center of mass of the object. Okay, so here's the definition of center of mass. Okay, you may already have a good idea of it, but the true definition is that the point at which mass is equal on all sides of that object. Okay, and you don't need to have this equation memorized, but this is kind of good to have the conceptual understanding. So the position of the center of mass is equal to mass 1 times the distance of that mass 1 plus mass 2 times the distance of that mass 2 plus mass 3, and so on, okay, over mass 1 plus mass 2 plus mass 3, and so on. Okay, so if I add up all the masses times the distances and then divide them by the total mass, I can determine the position where all the mass is going to be the same. It's going to be equal on all sides. So that's how we calculate center of mass. So here's just kind of a good conceptual problem. Where is the center of mass for this object? Okay, so we have a dumbbell, if you will, with 5 kilograms on this side and 15 kilograms on this side at 4 meters. Okay, so would the center of mass be at 1 meter, 2 meters, 3 meters, or 4 meters? Okay, so think about that for a second. Now, hopefully you picked C, 3 meters, okay? Because the center of mass is going to be closer to this object, okay, than it is going to be to this object, okay? If this was truly a dumbbell and you were lifting it off the ground like you normally lift weights, right? If these were both 10 kilograms, they'd be in the center. But you want to lift from the center. But with this side being heavier, you'd want to lift closer to this side. So the center of mass is going to be closer to this one than to that one. Okay. So what does this predict about the slinky drop? that means that the center of mass of the slinky will fall at gravitational acceleration. That's what we would expect from Newtonian physics, right? Newtonian physics, you drop the slinky or drop any object, it falls at the gravitational acceleration. So if I take the slinky and I drop it, or I look at the center of mass, I did this in class, if I drop the center of mass of the slinky at the same position as like a pen or any other object, they hit the ground at the same time because the center of mass is going to travel at gravitational acceleration. Okay, so it's really cool. So this is another key concept. The idea is that the center of mass of any object will behave according to the principles of Newtonian physics. So the things we learned in class are things for the center of mass of an object, okay? And some people think, well, this means we're not really doing much for calculations, but most objects are solid, so it works out pretty well. You know, we're not constantly changing shape and everything, so we're still doing very good calculations for what will happen, but we just have to be particular that this is only for the center of mass of that object, okay? And this goes for any object. So even fireworks, guess what? They're still going to behave according to Newtonian physics. So think about a firework. You shoot it up into the sky, and then it blows up to a million pieces. Okay, some people might say, okay, we can't do any physics after that point. But it turns out it still behaves according to Newtonian physics, or at least the center of mass does. So if I took up all the different pieces of that firework after it blows up, and then calculated the center of mass for that firework, it would behave like a normal projectile. So just like if I threw a ball up in the air and it landed back on the ground, guess what? If I took the center of mass of all those different firework pieces and all the different flammable materials, guess what? Their center of mass is going to fall in the same place as I would predict for any other object. Okay? So that's pretty cool. Okay, so no matter what the object, no matter what it does halfway through the air, it still is going to behave according to Newtonian physics. Okay? So going back to this demonstration here, the reason it can go uphill is because its center of mass is actually going downhill. So if you look at the center of the object and you look at the center of mass, when it's rolling up the hill, its center of mass is actually going down. Okay, so that explains why that works, because of the way it's shaped, the center of mass is actually going to go down, so it looks like it's rolling uphill. Okay, so that's just kind of a trick they use using that center of mass principle. Okay? All right, here's another key concept we want to cover. An object cannot support itself if its center of mass does not lie in the range of its base. Okay? What does that mean? Okay, think about like a chair. Okay? Just a regular chair. People sit on chairs all the time, right? They have four legs. Okay? The range of the base, as we call it, is the square that is made by those four legs. Okay? So if my center of mass is directly over any point on the square, then it's balanced. It can support my weight. Okay? So this is stable, and I'm sitting in the chair, and the center of mass is right here. The chair is stable. But if I try to lean on my chair too much, and my center of mass comes over here, outside the range of the base, guess what? The chair is going to tip over. Okay? So if my center of mass does not lie within that range, okay, if I take the kind of the square that's made by my base or the triangle or whatever it is, okay, whatever shape I make with my object, if my center of mass is not within that, then the object's going to tip over. Think about like a Christmas tree. I have a Christmas tree, and I just put it straight on the ground. It has a very small trunk. The center of mass is over here. Guess what? The tree's going to tip over. So that's why we put the Christmas tree in a large tree trunk base, right? Kind of those green bases you probably buy at the store, right? So then if the center of mass is over here, it can still support itself. Okay? So very important for architecture, for any type of materials we build, we want to make sure our center of mass is in a good location so that it can balance. Okay? If we're very particular, we can make the center of mass in a specific location. So I showed a demonstration class of this little bird that has a lot of weight on its wings, and it's made specifically so that center of mass is right over the beak of the bird. So the bird can actually balance on the beak, which is kind of cool. Because the center of mass just lies directly over it, it can balance because it fits on the range of its base. Okay, so that's a cool example. So based on this, can something like this work? Okay, so this is an old Michael Jackson stage performance. Okay, he is known for this trick where he leans like at a 45-degree angle, which is pretty much impossible for most human beings. So how does he do it? Because if you think about it, his center of mass is like probably right here. Okay, and that is not over his feet at all. Okay, so here's the range of its base. Okay, so how is he able to support his weight if he does that? So a lot of people just thought, oh, Michael Jackson must be really strong. Okay, but we know from physics that that can't be the case. He must have just tipped over, or he would just tip over if this was the case. But he actually made an invention for his shoe that would actually link into the floor. It was kind of a special bolt that would link into his shoes, and so then when you link into the floor, your range of your base is no longer your foot; it's actually the entire ground. So as long as his legs could support his weight, he could actually stand up, okay, because he's linked to the floor. So that's kind of a cool example of overcoming that center of mass problem. Okay, some other applications were things like karate. Okay, if you do karate, you'll learn that you always keep a very wide stance. And a lot of people don't understand, why do you always look so strange and stand with your knees apart? But it's actually a center of mass thing. So if you keep your feet apart, then the range of your base is the distance between your feet, this kind of rectangle shape you make. So as long as your center of mass is between your feet, then you will keep standing up. But if you stand like at attention, you can think of the army standing with your feet right next to each other, and then someone punches you, then if you kind of tip over a little bit and the center of mass drags out to outside the range of your base, then you'll tip over. Okay, so that's why you like to have this nice wide stance, so that your range of your base is large and that your center of mass will stay over it. Okay. Some other applications in sculpture. Okay, when they make sculptures, they gotta make sure that the center of mass lies over the base of the statue, and particularly the more feeble parts of the statue. For example, this one, if there wasn't this nice solid cylinder right here, this thing would tip over for sure. Okay, and even a famous example is in Michelangelo's David. If you look at the very base of David near his feet, Michelangelo put this tree trunk looking thing near his back leg. This wasn't because of any type of artistic thing, but Michelangelo actually left it in there so that the center of mass would kind of go over this way, and so the center of mass would be over David's foot, making it easier for the sculpture to stand up and it wouldn't break. And so that's actually a kind of science principle right there. He left that in because he knew if he didn't, it wouldn't be able to support the weight of the statue, and the center of mass would make the statue tip over. So that's a really cool example of how center of mass came into play with sculpture. Okay. All right, last of all, I want to do an example problem. This is kind of a fun example problem from Star Wars. Okay, so if you've ever seen Star Wars, the very original, or very first one, the original one, Episode 4, A New Hope, there's a scene where Darth Vader grabs this guy and he's trying to interrogate him, and he calls him rebel scum and basically choking him while he's in midair. And it's pretty cool and pretty intense. But from a center of mass perspective, this wouldn't make much sense, because if we look at this scenario, okay, Darth Vader is holding this guy up here, and he's not tipping over at all, which means Darth Vader must be pretty heavy to keep the center of mass over here. Because if they weighed about the same, the center of mass would be over here, and he'd tip over. So Darth Vader must have a lot of weight compared to this, normal guy. So this normal guy we'll call the rebel. Okay, so the mass of the rebels is just, let's say he's just a normal guy, about 150 pounds, so 73 kilograms. And if we set up these variables, then we can actually determine the mass of Darth Vader. Okay, and I don't expect you to do the math, but when you actually do it out, it's kind of funny. It turns out Darth Vader must weigh about 260 kilograms, or 500 pounds, more than 500 pounds. So that must mean his suit's pretty dang heavy. So anyways, that's kind of a fun example of how the center of mass can help us in situations, and we can calculate that out. And the last thing we did in class is the little mini lab about the center of mass, so make sure you go to the website and print that out if you didn't do it. But that's all we covered for center of mass. Again, very interesting topic that we sometimes overlook, but let me know if you have any questions, and thank you for watching.